Welcome to today's webinar, Drone Simulation for Urban Air Mobility, brought to you by CONVERGE Science. Thank you for joining us today for the fourth installment of the 2024 CONVERGE webinar series. My name is Mattia Sulis, and I am part of the business development team at CONVERGE Science. I will be your host for today's event. I'm glad I can be here with you today and learn directly from our partner CycloTech GmbH about drone CFD modeling using CONVERGE. CONVERGE Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. CycloTech GmbH is the world-leading company for aviation propulsion system based on the Voigt-Schneider principle. The Austrian company has developed the unique 360-degree thrust vectoring cyclorotors, a new electrically driven, sustainable, and high-maneuverable propulsion system for the new air mobility demands of the 21st century. The complex design and unique 360-degree thrust vectoring of the cyclorotors enables an easy transition from hover to forward flight profiles with gas control and precision landing. This is ideal for safe operation in crowded airspace and confined areas. CycloTech aims to make individual air mobility as normal as driving car, opening the sky for everyone. Now it is time to introduce our speaker for today's event, David Karman. David has been an aerodynamics engineer with the focus on CFD simulation at CycloTech GmbH for 2.5 years. David graduated at Delft University of Technology with the specialization of ship's hydromechanics. During his studies, David worked on Voigt-Schneider propellers, and now he is applying his experience with cyclodial propellers at CycloTech GmbH. Before joining CycloTech GmbH, David has worked at CONVERGE Science GmbH as a CFD research engineer for 2 years. Without any further delay, I will now pass the ball to David. Thank you all.
Thank you very much, Mattia, for the warm welcoming, and welcome everyone. It's a pleasure for me to be here and to speak about CycloTech and also about how we utilize CONVERGE CFD for our cyclorotor simulations. In this webinar, I will briefly introduce you the company, and then after I will give you a short theoretical background regarding the working principle of the cyclorotor. In the second half of my webinar, I will bring you the CFD results. I also prepared with 3 different CFD example cases. I hope you will enjoy it. So let's start. CycloTech is an aviation propulsion technology company which is a global leader in the development of cyclorotors. The headquarters is in Linz in Austria, and it is rapidly growing with currently now more than 50 employees. I can tell you when I joined CycloTech 2.5 years ago, we were less than 20. So it really has this buzzing startup environment that actually I really like. Our main focus is the cyclorotor. Currently, we are developing the 6th generation of our cyclorotors. We granted 5 different patents. We own a highly automated tool chain, and we have accessibility to indoor and outdoor test areas. As Mattia mentioned, our vision is open the sky for everyone, or let's say make individual air mobility as normal as driving a car. And we truly believe that the best way for this is powering the future eVTOL vehicles with our cyclorotors. We have a fully developed flight demonstrator, which weighs around 80 kg and equipped with 4 cyclorotors. The first free flight was in August 2021, and from that on we conducted more than 800 flights. As you can see, this demonstrator can safely take off, land, and maneuver. Apart from the proof of concept, we also have feasibility studies. One of the major ones was the eVTOL cargo drone, which was a joint feasibility study with Yamato Holdings. Yamato Holdings is one of the market leaders for parcel logistics, and they could benefit a lot from an advanced aerial vehicle with high maneuver capability. For that purpose, we designed together the drone, which is depicted here, and it has a 45-kilogram payload and could fly up to 40-kilometer range. Both parties, Yamato and also CycloTech, published a white paper about it. So if you are interested, I encourage you to reach out these papers and read them. After the Yamato cargo drone, we decided to come up with our aircar study, and this is how the Cruise Up was born last year. Cruise Up is an aircar concept with 6 cyclorotors, and as you can see that 2 of these cyclorotors are placed in the longitudinal, along the longitudinal axis of the vehicle. Because of this, the vehicle can easily go sideways without tilting the aircar. This is a quite unique feature with eVTOL's aircars. The top speed of this vehicle is 150 km per hour, and it has a range of 100 km. The 6 rotors also increases the redundancy of this vehicle, so in the event of one rotor failure, the aircar can land safely. Before going to the CFD results, I would like to introduce you the working principle of our cyclorotor. And I would like to do this through our demonstration video. So actually, a cyclogyro has several blades rotating around a center rotation axis. These blades are connected to a central hub via conrod, and the hub itself can rotate freely. Moreover, its center can be dislocated eccentrically with regard to the center of the cyclorotor. An eccentric position of the hub causes periodical change of the angle of attack of each wing during one revolution. This accelerates the airflow through the rotor and results in a thrust. The distance between the rotation axis of the rotor and the rotation axis of the hub determines the thrust magnitude, while the position of the rotation axis of the hub in peripheral direction determines the thrust direction. To sum up, cyclorotor is the most agile, precise, and compact propulsion system. With its truly 360-degree thrust vectoring around the rotation axis, it delivers smooth transition from hover to forward flight. And also, it provides superior maneuverability and gas control. Finally, we arrived to the CFD part of this webinar. I think this will be the most interesting for many of you. First, I would like to show you the areas where we use CFD at CycloTech. Then I will speak about that, what are the things that we benefit the most from CONVERGE. And as I already mentioned, in the end, I will show you 3 example cases. 2 of these example cases will be with a Cartesian mesh, but one with the acoustic analogy, and there will be an inlaid mesh case as well. So, at CycloTech, we do hover simulations, which means simulations with incoming speed. But we also do simulations with incoming flow. This is what we call forward flight simulations. Of course, we are aiding our design constantly with wind tunnel tests, and we also use these wind tunnel tests to validate our CFD results. Noise is a very important topic for us because we would like to gain public acceptance, and we would like to produce an as silent as possible rotor. Therefore, we also do computational aeroacoustic simulations. If we are talking about rotor development, optimizations is a must. We do wing, rotor topology, and pitch curve optimization. Finally, we also use CFD for flow control solutions. So, our cooperation with Convergent Science started in last year, May. So we can say that we are relatively new users of Converge, but there are already many things that we like. The first of this is the user friendliness and the ease of use. So I guess if you ever used Converge, you know that basically you can learn the software within an afternoon. And basically this is what happened at our company as well. So colleagues without any practical experience of CFD started to use Converge and CFD, and we could therefore increase our productivity. Of course, after using Converge, we don't want to make mesh again. We benefit a lot from its autonomous meshing, and we also really like the Adaptive Mesh Refinement feature. Another feature which is very important to us is the easiness of introducing complex motion profiles. I guess you have seen that our pitch curve is quite elaborate, but even this elaborate pitch curve can be easily introduced to the software, for instance, in tabulated format. And what is also very important, that the outputs and the inputs of the software are in a well scriptable format. We have custom-made post-processing scripts that I will show you the results, at least not the scripts, but the results later. We use aeroacoustic models and turbulence models from physics, so we don't use a lot of physics models from Converge, but we are satisfied with what we are using. And we also use advanced features. One of it is the acceleration methods, like the grid scaling. You could see on this video that there was a grid scaling after 140 crank angle degree. And we also use inlaid meshing. And now we arrived our first example case, which will be a wind tunnel validation case. In all of the example cases, I will present you a cyclorotor geometry with 5 winds. What will change from example case to example case is the speed of rotation, the incoming flow speed, and also the dimension of the rotor and the simulations. With the inlaid mesh, actually the dimension will be just only a 2D. It's a 2D case. What is also similar with all cases, that we will place the rotor in air with 15 degrees Celsius. If we are speaking about cyclorotors, advance ratio, abbreviated here as AR, is a very important dimensionless number, which is basically the ratio between the incoming flow speed and the rotor peripheral velocity. Many of you might be more familiar with the term tip speed ratio, which is widely used in the wind turbine industry. I can tell you that the advance ratio is the reciprocal of the tip speed ratio. Another important definition for us is the offset angles. Here you can see on this schematic picture that what is the offset angle, which is here. So actually, basically, it is just the angle of the incoming speed. Please note that this is just a schematic picture here, so it has nothing to do with this other rotor. You can already see this from the number of rotors. There are only 4 rotors here. In this wind tunnel validation, we tested offset angles from -30 to 10 degrees. We used a spherical domain of a diameter of 200 meters. And we filled up this domain with a Cartesian grid with a size of 2.2 million cells. We designed the mesh such that the final mesh size is 1 millimeter, and this resulted in an average Y plus of around 50. For the turbulence model, we used the large eddy simulation, namely the LES sigma closure. For validation, for this example case, we use the thrust and the lift coefficients, and we also use the power coefficients as function of the offset angles. Let's have a look at the results. In each results, there will be two set of curves, 1 and 2, and this is because we simulated this case at two different pitch curve. So in all graphs, the dashed black line will represent the experimental results, while the solid green will be responsible for the CONVERGE results. What you can see that with the CTCR parts, the trends are well captured. There is an exceptionally good match at advanced ratio 0.25 here. However, if we have a look at the power coefficients, we can see that unfortunately the power coefficients are hugely overpredicted. We wanted to know that why we have this overprediction, so we decided that we will do a deeper analysis with the flow field. First, we created this animation of the crew criterion isosurfaces to understand better the flow structures around the blades. I guess you can already see that there is a huge detachment region here in the frontal side of the rotor. But if you little bit more look behind the shaft, you can actually see another detachment region over there. To see this detachment region better, I also marked them, and I also brought here the total force coefficients as a function of azimuthal position to see the impact of this detachment. What we can see, the frontal detachment produces a deep stall, so actually for the wing is really hard to make it there. So the flow is really hard. For the flow is really hard to reattach to the wing, and with the red area, the results are a bit different. Because basically what is happening here is that there is a detaching vertex from the wing in front of the coming one, and this is producing a very favorable upwash on the wing, and that's why we are seeing this peak in the total force coefficient. As a CFD enthusiast, I love these structures, so I think they are beautiful. But we wanted to be sure that what we see is realistic and it's not coming from the lack of grid resolution or not coming from the fact that we try to resolve a highly unsteady case with a Cartesian cut cell method in the boundary layer. First, we decided to refine the mesh. Well, not on the blade, but in the close vicinity of the blade, because anyway, this was necessary for the next topic, which is our noise validation. So, as you know that noise is a very computationally very resourceful topic, you need to have a very high grid resolution in order to have a good resolution with the acoustic waves. We used at this example case the same rotor as we did with forward flight, but as I mentioned, it is a Hoover case, so there is no incoming flow. The domain here, it's a cylindrical one with a base of 200 meters diameter and a height of 80 meters. This big domain helps us to not to have a lot of reflection from the outer boundaries. We also designed the mesh such that there are very big cells close to the outer domain, which helps us to dissipate the acoustic waves in that region. As I mentioned, we did not refine the mesh on the wings, so the finest mesh size is still 1 millimeter. But as you can see, we made a very fine region around the rotor. The average Y plus resulted in 45 with these settings. we still use the LES sigma turbulence closure. In acoustic simulations, not only the grid resolution is important, but also the accuracy of the discretization scheme. We use the second-order central spatial discretization in order to eliminate the numerical diffusion from our simulations. And we also made the mesh such that at least there are 20 points per wavelength up to the 8 basepassing frequency within the permeable surface. We did this to reduce the numerical dispersion. And if I mentioned permeable surface, then you already know that we were working with a hybrid acoustic analogy. So basically what we do that we model the flow in a very fine mesh inside the permeable surface. And with the help of Ffowcs Williams-Hawkings acoustic analogy, we propagate these acoustic waves to the desired distance. And this distance in our case was 10.8 meters. For validation, we will also have a look at the total force coefficients and the power coefficients. For the results, I will present three sets of different results. The one which will be denoted with the color blue is coming from our outdoor test. We carried out this outdoor test in 2022 in an airport close to our site. The setup was such that the closest reflective surface was at least 200 meters away from our rotor. We placed microphones all around the rotor at a distance of 10.8 meters. The next set of results will be the indoor test results, and they will be marked with a black color. You can see that the microphones here are closer. They are just 5.1 meters away from the rotor, but the results anyway were recalculated to 10.8 meters. You can also see that we did not use acoustic panels, so these results are polluted with reflections. And finally, the CFD cases will be represented with a red color. The first two results that we can look at is the total force coefficients and the power coefficients. Here we only have results for validation from the indoor test case because these values were not measured with the outdoor measurement. What you can see that CONVERGE follows very well the total force coefficients for different maximum pitch angles. However, with the power coefficients, we see similar trends what we have seen in forward flight, that at high pitch angles, the results start to deviate and CONVERGE overpredicts the CP. Finally, let's have a look at the sound pressure levels as a function of maximum pitch angle. Here on this graph, the sound pressure levels minus the sound pressure levels for a zero pitch case is depicted. What we can see that the smoothest results are created with the indoor test, and we believe that it is because the lack of background noise. Of course, whenever we are testing outside, the wind is always there. The wind is always there, and we should not forget that we were at the airport, even though that we tried to measure when aircrafts were not passing by, still there was some background noise. So what we can see that the outdoor measurements are also following the trend of the indoor one, but they have a bit bigger scatter. And finally, CONVERGE has the biggest scatter, but the trends are still captured, and we are quite happy with it, that considering that this is the first time we are doing an acoustic analogy with the cyclorotors, we believe that these are quite good results. Of course, if we are talking about acoustic, we would like to see that how is the acoustic spectrum of the simulation. And here we can see the spectrum from the smallest to the highest maximum pitch angle. What we can see that when the pitch is low, that the mechanical noise are becoming quite important, especially in the indoor test. So not to forget here, the microphones were closer to the rotor, and also the results are polluted with reflections. I would therefore say that CONVERGE more follows the trend of the outdoor test, especially here. You can see that the broadband noise is very well resolved. And we are happy that the dominant tones are captured accurately, but they are a bit over-predicted. And quantitatively, I would say that the results are with the tones, results of the tones are closer to the indoor test. We also wanted to see that how the noise is perceived in space. So we created directivity patterns. This is a directivity pattern for the highest pitch angle for 51 degree. What is depicted here is the directivity pattern of the first blade passing frequency. So it is the sun pressure level at different azimuthal angles minus the average sun pressure level over the perimeter. What we can see that the trends are kind of captured, I would say. Well, let's not forget about that this is the most challenging case, but to be sure, I see, to be fair, I see room for improvement. But as I already mentioned it to you, we have quite many ideas how to improve further these simulations. Before moving to the inlaid mesh case, I would like to show you the animation of the flow field. On the top row, you can see the animation of the normalized velocity model, while on the bottom row, you can see the force vectors over the cycle and also the direction of the total force. By the way, I should mention that these top row animations were created with our custom-made post-processing script. So this is a good example that that shows that how good are the outcomes from CONVERGE for making scripts with them. What you can see that if we are looking at from the lower to the higher pitch cases, that the flow field is dramatically changing. With the low pitch, we don't really see a designated wake, while with high pitch, the wake is very well demarcated. And what we also can see that we still have these vigorous detachment regions here and there. So to finally find out that whether these detachments are the responsible ones that the simulations over predicting a lot the power, we decided to do an inlaid mesh simulations. In this inlaid mesh study, we again use the hover case, so there is no incoming speed. We reduced the RPM to be 2,700. But what is more important here is the span of the rotor, which is now just 5 centimeters. Or let's say that we ensured that the domain is as small to the third direction that there is only one grid cell in the spanwise direction. Or in other words, this is a 2D case. At top, bottom, and side walls, we use the symmetry boundary conditions, and we choose for the diameter of this disc to be 33 meters. The finest Cartesian mesh size was kept at 1 millimeter, but thanks to the inlaid mesh, we could manage to bring down the average Y plus to be 2. For turbulence, we use the Spallart armorers or the SST models. Here you can see a picture of our inlaid mesh. We pushed the growth ratio until 1.2, and altogether we had 19 layers. For validation, we used the power coefficient. Here you can see two animations. On the left-hand side, a case without inlaid mesh, and on the right-hand side, a case with inlaid mesh. Both of them for the maximum pitch amplitude or the maximum pitch angle, which was the 51 degree in the previous case. As you can see, that no surprise here, the no inlaid case is producing these detachments here and there. If we have a look at the inlaid case, we can still see detachment here, but not as strong as without the inlaid case, and we don't really see any detachment here. So to again look together the flow behavior with the total force coefficients, what we see that thanks to the not strong detachment, the flow recovers much faster, it reattaches much faster in this region. And in this region, we don't see this very strange peak in the total force coefficients. What did bring us these results for the power coefficients? Well, actually, I can happily tell you that with this solution, the overprediction of the CP radically reduced. Now it's only just 12%. And I think considering that this is a 2D case, this is a very, very good result. So arriving at the end of my presentation, let's have a wrap up that what I was speaking about. We have seen that CFD aids and simplifies the aerodynamics design of our cyclorotor. We also saw that how CONVERGE brings numerous advantages for our design process. We benefit a lot from the advanced meshing techniques, grid scaling, AMR. These are all techniques that we are using every day. And I was very happy to see that how inlaid meshing increased the accuracy of our simulations. As you saw, we don't use a lot of physics, but what we use, it's working well, so which is always good. And we also really like the custom-made scripts that we can do with CONVERGE. What I was not speaking about, but is important, is the excellent parallelization of the software on our HPC and the world-class support service. What's coming next for us? We are very excited to extend the 2D inlaid case to a 3D inlaid mesh simulation. We would also like to test the software for multi-rotor simulations. We would also like to do with CONVERGE wing force validations. And of course, at one point in the future, we would like to use the software for rotor and wing optimization. With this one, I arrived at the end of the presentation. I hope you found it to be interesting. If you liked what you have seen, you can always follow us on social media. We are on YouTube, LinkedIn, and also on Twitter, which is now called as X. So thank you for your attention, and I'm looking forward to your questions.